Welcome to Plutus, and today we are covering Joule-Thomson's effect. Now, what is Joule-Thomson effect? Joule-Thomson's effect explains what will happen to a gas if it undergoes adiabatic expansion, whether it will get heated, whether it will lose heat. This can be explained by a simple experiment conducted by scientists Joule and Thomson, and collectively we are using their surnames for reference, that Joule-Thomson. For their experiment, the primary condition that you need to take into account: first, this only relates to your adiabatic expansion of a gas. Adiabatic expansion, whether real or ideal expansion of gas. For every single adiabatic expansion, the change in heat for the system will always be equals to 0. Okay, now since we know from the first law of thermodynamics, that du is equals to dq plus w. Here, since dq is 0, that simply means whenever a gas, whether it expands or contracts, whatever the work is done by it, it will directly leads to the increase in the reactivity of that species or the system. There will be no loss of heat or gain of heat. Whatever the heat generated, it will directly leads to increase of internal energy of the system. Now, in order to prove it, Joule-Thomson did an experiment. Okay, they took a container which is completely made for adiabatic processes. That means in the system there is neither gain of heat, neither loss of heat. Now, this system is connected with two thermometers T1 and T2, which will measure when I have a gas in chamber A of the compartment separated by a porous plug, and when it moves to chamber B. Preferentially, the gas you are taking in this, it will always be at a higher pressure. While on the chamber B side, either the pressure is maintained very low or we ensure that it exists on vacuum. Now, here, since the moment you start adding a little pressure, this throttling mechanism starts to move from left to the right hand side. When it moves, the gas still has some pressure and it occupies some volume. So it will have pressure PA and volume VA. When it gets passed through the porous plug, from this porous plug, some portion of the gas moves to PB and will have a volume VB. From left hand to right hand side. Initially, we are maintaining a very low pressure or vacuum. So initially there was no gas present. But when you apply throttling mechanism, some of the gas starts to pass from chamber A to chamber B. Now, since heat cannot pass through this entire system, this gas moving from A to B utilizes that energy to increase its internal energy, and moving from A to B, this gas expands because previously it had only this much space which it was occupying. Let me use a different color to represent it. Here it is occupying only this much space, but when the piston moves, let's say the piston moves here, now it has some higher volume. So the piston that you are taking, you need to also be very cautious that it should be a frictionless or weightless. We are assuming that because when the pressure is applied in the system's internal energy is increasing, we are assuming that friction and weight of this species is not contributing to the change in internal energy of this particular system. Now, assuming this to be an ideal gas, the initial and final temperature measured by thermometer T1 and T2 always remains the same, which means the delta T value for ideal gas will always be equals to 0. But for any other gas, any other gas that we are having, it will be Tf and Ti can never be equal. So there will be some change in temperature of the gas. Previously we have seen that dq is equals to 0, which is equals to du minus of dw. Du I can write it as 0 equals to u2 minus u1, while dw, the total work done, I'll be utilizing it instead of going for this dw. The total heat change, which is the delta Q, will remain 0, while the total internal energy change minus the total work done by the system. To find the work done by the work done in chamber A, work done by system to compress the gas in chamber A, to compress gas in chamber A. I'll be writing it as WA. The pressure was PA. Now, the initial final volume of the gas, wait, the PA, it will be final volume minus initial volume. For compression of the gas, it will be VA minus 0. For similarly, when the gas moves to chamber B, the pressure changes to PB. Finally, what happens is when this entire gas is pushed from chamber A to chamber B, the final volume of the gas will become 0, and this will be VB. This will give us PA VA, and this will give us PB VB. Here, this plus sign in front of PA VA represents compression of the gas, while this negative sign here, it represents expansion of the gas. The gas is now expanding. Initially, it had some value VB, finally it becomes to 0 when it finally gets to expand completely. So the total work done would be WA plus WB will give me the total value of work done W. Putting in the values, PA VA minus PB VB. Putting everything in the equation back to, so du is u2 minus u1 minus work done PA VA minus PB VB. It will be equals to 0, u2, separating the variables, it will become minus plus of PB VB, which is your internal energy in the chamber B, and I'll be writing as at enthalpy number 2 in the chamber second. This I can write it as, let's mark it as UAUB, much easier, and this will be enthalpy of the chamber A, chamber B, and I can write minus of UA PA VA, which will be enthalpy of chamber A. Combining this, we find that it is HB minus HA. That means HB is equals to HA, or you can directly mean that delta H equals to 0. So Joule-Thomson's experiment suggests whenever a gas undergoes adiabatic expansion, there will be no change in enthalpy or the process is isothalpic in nature. So since there is no change in energy, so that means whatever the energy you are having, it will be directly utilized to increase the internal energy of the system. We also know that enthalpy is a function of temperature and pressure. And if you try to utilize it in form of cyclic rule, I can write it as dH by dt constant pressure. Using cyclic rule, I can write this as dH by dP at constant T multiplied with dP. Now, for according to Joule-Thomson's effect, Joule-Thomson effect, here the dH is an isoenthalpic process, so dH will be equals to 0. Separating these two parameters, it will be equals to dH by dt at constant pressure minus dt equals to dH by dP constant T to dP. Here, enthalpy change per unit change of temperature at constant pressure is called as heat capacity at constant pressure, molar heat capacity. Switching the value, separating, it will be dt minus of 1 by Cpm, and this will be dH by dP at constant temperature. Dividing everything, this will be dP dividing by dP. It will become dt by dP. Since this entire process is occurring at isoenthalpic process, so at constant enthalpy, minus 1 by Cpm dH by dP dt. dP will get cancelled out, and this entire value of dt by dP is called as your Joule-Thomson coefficient, which will help us to predict the behavior of a gas under adiabatic expansion. Now, if you take mu Jt, you can simply written as that mu Jt is what? Change in temperature per unit change of pressure. Delta P. For expansion, the delta P is always equals to negative. So, whatever the value of mu Jt you are having for a gas, by calculation or experimental methods, you can predict the behavior of the gas under expansion. If mu Jt comes out to be positive, the only way mu Jt can be positive is when delta T comes out to be negative. That means final temperature minus initial temperature should be equals to 0. If that's the case, so that means the final temperature of the gas would be lower compared to initial temperature. That means a gas having positive value of mu Jt will get cooling effect under expansion. This is the case for most of the gases. If mu Jt turns out to be 0, it simply means that the gas follows ideal behavior. That means it's neither getting heated nor getting cooled down. Last option, when mu Jt turns out to be negative. If it's negative, that means delta T was positive. That means final temperature minus initial temperature is greater than 0, which is only possible when the gas gets heated. So by simply measuring the values of mu Jt, we can predict the nature of the gas under expansion. Now this is one of the most important things that comes into use of daily life, especially when it comes to refrigeration processes. For example, your ACs, refrigerator, they all work on the concept of Joule-Thomson effect. What type of gas that you are taking as a refrigerant? For example, ammonia. Ammonia is one of the most common refrigerant that is used as a refrigerant material. Because of hydrogen bonding, it can easily absorb heat, which leads to a positive value of mu Gt. So I hope this would have cleared all your doubts regarding Joule-Thomson's effect and you have learned something new. In case of any doubt, you can add it to the comment section and we'll get back to you. Thank you for joining us.